Assalamualaikum and good day. Today we're going to start with our chapter 4, okay, which is Laplace transform, part 1. Okay, we will start with the outline of this chapter 4, which is for chapter 4, part 1, is the introduction, okay, where you will introduce to time domain function and frequency domain function, followed by number 2, which is definitions of Laplace transform, inverse Laplace transform, properties of Laplace transform, and circuit analysis. Okay, so this is photo of our UTMKL, okay, the residential of UTMKL. So introduction, transformation from the time domain, which we call as T domain, as you guys know, in which inputs and output are a function of times. Okay, this I believe that you guys are well aware already. To the frequency domain, which is our F domain. Okay, where the same inputs and outputs are function of complex angular frequency, which is a radian and unit time. Okay, so you see in the F domain, okay, the same input and output can be a function of complex angular frequency where you can have a radian and unit time. So later on we will see provides an alternative functional description that often simplifies the process of analyzing the behavior of the system. Okay. Application in engineering, Laplace transform is used to solve complex differential equations. Okay, if you can see here, Laplace transform is actually for you to solve differential equations. Okay, differentiations. Okay, that used to model an engineering system. Okay, so maybe in the previous chapter we don't really touch on differential equations. Okay, also used to generate the transfer function representation of systems such as electric circuits and control system. I believe if you have taken control system, you will see some of the differential related formulas. Okay, the transfer function representation give an algebraic relationship between the Laplace transform of the input and output of a system. As you guys know, transfer function is actually the relationship, okay, between the input and output. Between input and output, we have a transfer function, the one that going to transform the input to the output. So the output can be the same as input, or the output can be totally different from the input. Depends. Okay. Next, to solve this Laplace transformation, we consist of 3 steps. Okay, we follow 3 steps. First, Laplace transform operation will transform the differential equation. Okay, will transform the differential equation in your time domain to the S domain function. You see here, Laplace. Laplace is represented by the S domain function. Okay, the equation in S domain will be solved by using conventional algebraic solution. Okay, the inverse Laplace transform is then used to change the solution in S domain to the T domain function to produce the desired differential equation. If you guys can see from the Fourier transform, even we have inverse Fourier transform in order to obtain the T domain back, right? So the same goes for Laplace transform. We have inverse Laplace transform in order for us to obtain the T domain again. So by using this method, Laplace transform made the solution for the differential equation much easier. Okay, let we see from our appendix, okay, from our appendix where is actually our Laplace transform lies. Okay, you refer to your appendix. Okay, it's on the appendix 16, right? So you can see here the Laplace transform. So we will still cover the same, but for Laplace differential equation, for differential equation scenario. Okay, linearity, time shift, frequency shift, time scaling, time transformation, modulation, convolution, differentiation, integration, multiplication by t, initial value, and final values. So here also given the Laplace transform pace, okay? If you see the signal in ft, for example, it is in impulse. But when we do the Laplace transform, we will obtain a value of 1. And for example 2, we given in impulse with a time shift, then we will have a 1 here times with a shifting given by negative as, okay? Your shift a in time domain will translate to shifting in will translate to a at our exponential for our Laplace transform equation. And for as here is you see in the time domain you are given, for example, if you have unit step, if we do the Laplace transformation, we will obtain 1 over s. The same goes for everything below here for similar. Okay, you guys can refer later on. We continue. Okay, now we're going to see the difference, okay, the different compare on contrast between your Fourier transform and Laplace transform. Okay, firstly, Fourier transform, both signal in time domain and its spectrum in frequency domain are 1D complex exponential. So it's 1D, okay? In Fourier transform, if you see the word here, in time domain and its spectrum in frequency domain are 1D. So this is the main difference. While in Laplace transform, complex function defined over a two-dimensional complex plane. Okay, we have two-dimensional complex plane now. We call them as S-plane, spanned by two variables. So you will have real and imaginary axis. Okay, in Fourier transform, we don't have that. Okay, it's only 1D. Here is complex plane spanned by two variables, real and imaginary axis at your S-plane. Okay, for Fourier transform, convert time domain signal into frequency domain in the function of your angular frequency, which is you call this as omega. Am I correct? Angular frequency is omega. While in the Laplace transform, we convert time domain signal into frequency domain in the function of complex angular frequency. So it's a complex, okay? Complex means you will have real in imaginary values. Used for Fourier transform, used for converting non-periodic signal, as you already know, right? Chapter 3, into its frequency spectrum for manipulating them in frequency domain. So it is a non-periodic signal. However, for Laplace transform, it is used for solving problem involving differential equation and integral equation. Okay. Next, time domain function. Okay, expression or equation that relates to time. This one is very straightforward because it's time domain, right? So it is expressed in t. A change in time will cause a change in certain variable, certainly. For example, of time domain function, we have xt equals to t plus 1. So if you t is equals to 0, you will have xt equals to 1. And if your t is equals to 1, you will have x1 equals to 3. Same goes for this exponent function. So example 1, time domain function. Okay, differential equation in time domain forms. So if you see here, dy t over dt plus 2yt 3t. So this is the first order differential equation, right? Next, we have d square yt over dt square minus 3 dyt. So here you can see the maximum is actually square. So this is square differential equation, okay, in time domain. So if RT in B0 here, okay, if you RT here having value of 0, mean this equation is actually homogeneous. Otherwise, if your RT here having a value So it is a non-homogeneous equations. So I believe that maybe you have learned this from, in mathematical subject, differential equation, if I'm not mistaken. Okay. So we have condition for RT here. If it's a zero, it is homogeneous. If it's non-zero, it is a non-homogeneous equations. Next, we go to this frequency domain function. Okay. In Laplace transform, frequency domain is called S domain. Okay, so don't use omega domain. It is S domain. I mean, you don't put here omega, you put here S. So first is a time domain signal. If we do conversion, which is Laplace transform, we will have capital Y with bracket S to show it is a Laplace transform produce signal. And if you want to obtain the time domain signal back, we do this inverse Laplace transform. So Laplace is shown by capital L. Okay. If you go to your, or it is not shown. Okay. Wait for a while. Okay. So if you have a time domain signal, right? For example, this YT. Okay. So if you convert, okay, if you do Laplace transform, because here is L. Okay. L. Then you will have obtained a capital Y and S to show you this is Laplace of undergone Laplace transform. And if you want to do the inversion process, inverse Laplace transform is a L power of -1. Okay, something like this. Okay, so this is inverse Laplace transform. This is Laplace transform. Okay, manipulation of mathematical equation is done in S domain. The real answer in time domain is obtained from inverse Laplace transform. Okay, you do Laplace transform to obtain your T domain signal from your Laplace equation. Okay, so here is a differential integral equation solution in S domain and time domain. So if you see here, this is your time domain signal, time domain region, and this is your frequency domain regions. Okay, let's say you have differential integral equation which is in time domain. Okay, you will do Laplace transform in order to obtain the transform function which is in Laplace in S domain. Okay, and then you can do algebraic manipulations, which in turn you will have a modified transfer function. Okay, so this is all in frequency domain, and then you perform inverse Laplace transform in order to obtain the solutions in the time domain. This is T domain. Okay, classical solution from differential equation integration equation to the solutions. Okay, next we go to the definition of Laplace transform. If your ft is a function in time domain t, means small ft, which is this, okay, where t greater than 0, greater or equal than 0. You must see here, right? It is greater or equal than 0 here. This is very important. Its S domain function is obtained by this. So you have f, capital F with S to show that it is a Laplace transform signal. L is a Laplace transform of f your t, small f and t domain. Integrations from 0, because here is t greater than 0, to your infinity. Then ft is the time domain signal, multiply with exponents of negative st with respect to dt. Okay, so this is that I showed just now is the Laplace operator. Okay. Example 2, given ft equals to 1, where t is greater than 0, find the function of ft in S domain. Solutions: If you see here is fs, you write it L in bracket f of t, and then integration from 0 until infinity, and ft times e negative st dt. Then you know that your ft is actually equals to 1, so it's actually 1 here. So it can be, we don't need to write 1. Then integration with respect to e negative st dt. Okay, then you do the integration accordingly, then you obtain 1 over s. Okay, so you go to here. Okay, if you see from Laplace transform pair, okay, if the value is provided, I mean if the is provided here, I mean some guidelines, you can refer to here. Okay, you can refer here to see this similarity that you can take. Otherwise, if there is no direct solution, you need to manipulate in order for you to have the signal which is finally look like this part or this part. Okay, I think you know this, right? Okay, you need to do some algebraic manipulation in case the direct equation given is is not in any way shown here. Okay, but you can obtain them if you do algebraic manipulations. Okay, so you see here, given ft is equals to 1 where t equals to 0. So this one is actually look like a unit step. Am I correct? Because we have 1, okay, where we only have value of 1 for greater than 0. So this one is actually like a unit step. Am I correct? So if you see a unit step, okay, you see from the table here, you see you have the unit step. So it is equals to 1 over s. So similar to the solutions here. Okay. Next, example 3. Find the Laplace transform for ft equals to 3e70 where t greater than 0. You see, again, it is t greater than 0 because it is greater than 0 for the Laplace transform equation formula, general one. So here, you can solve mathematically. 3 you can put outside, then you have the exponent 70 minus st. So you do some mathematics, then you get 3s minus 7. Okay, and then let's see if we have actually this in our table. You see here, we have this in our table, s plus a. Okay, so here is s minus 7. Okay, you can use directly from the table if there is directly the information. Okay, if no, you need to do algebraic manipulations, or if you want the no more complicated step is that you do the integrations. Okay, just try to see what is the fastest ways that you can actually solve the uh, situations or the problems. Okay, so Laplace transform, you need function tables. Okay, this one I shown just now from our table. Okay, so you can refer to here. Am I correct? Okay, for example, sine omega t, you can have sine omega t ut. You see ut here to show that it is greater than 0. So you have omega over s square plus omega square. So it's the same here. Okay, no need to memorize for the table, but it's good if you have some understanding. Okay, to use the table. Okay, you need to know to use the table because it will help you in the exam or test or quizzes. Okay. Example 4, find the Laplace transform for the function below by using the table given. If you have ft equals to t, okay, so this one is actually tut, so it's like a ramp signal. Okay, this one is like a ramp signal. It's a t times ut because we want it to be greater than 0. So refer to here if we have things that's related. So you have here t ut. So it's actually n factorial over Sn plus 1. So in our case, it's T1. So S1 plus 1. So it's S2. So this why you have S2. In fact, 1 factorial is 1. Okay. So similar to this, try to refer to table. Okay. Next. inverse Laplace transform is we're going to have this transform in Laplace transform domain into our ft domain. Okay, so you see here f small with t inverse of Laplace fs equals to 1 over 2 pi j. Okay, from negative j infinity until your j infinity, and your fs times est ds. So you can see it is here multiply with 1 over 2 pi j, and then expand from integration with a range from negative j infinity to your j infinity. Okay, and then your fs time your est and ds. Okay, so you see here, right, it is SSS domain. Okay, because your question is actually first the Laplace transform is in S domain, right? That's why we have integrate with respect to S, and don't forget we have J here. Okay, now determine if Fs, okay, determine Ft means that Laplace transform if Fs is given 3 over S square. So again, you see here Ft inverse Laplace of Fs and L negative 1, and you have 3 over S square. Then 3 you can put outside because it's just a just just a constant, and L negative 1, then 1 over S2, and you get 3t. Okay, and you get your 3t. You see here, if you see this is the question is 1 over S2. Okay, 1 over S2, you can see this is 1 over S2, so your t is actually 3 to the power of 1 times by 3, because the 3 is the constant, so 3t. Okay, you can see, right, directly is related to the table. Okay, make sure you know how to refer. Okay, next, given your fs equals to 1 over s plus 1 and of gs equals to sfs, find your gt. Okay, find your gt. So here gs is actually s times fs. You see here, gs is actually a multiplication of s times with your f Laplace transform of f. Okay, so s over s plus 1. Okay, then here you need to do some algebraic manipulations, okay, in order for you to have the common form that you can refer directly to the table. Okay, okay, where is the equation just now? So you have your s and you have s plus 1. Okay, you try to see from the table first. Okay, okay, you try to see from the table, you have this s plus 1, but you don't have at the top which is s, and also s plus constant below. You don't have that, or this one is different. Okay, this one with n factorial. So you need to know how to do algebraic manipulation. Okay, this is one of the step, right, shown in the previous in the previous flow. So what can you do in order to have this 1 plus s? Okay, s plus 1. Okay, you need to do this, but how to obtain that this to transform from here? Okay, how to do that? This one I left it to you, okay, in order for you to try. Okay, this one is you already do from your previous mathematical subject. Okay, how you actually able to split this? Okay, how you actually able to split this form? Okay, because you should know that something that this function multiply with some function in order to have this equation back. Okay. Or maybe I can do it for you. Okay. Okay. Here is s plus 1 and s plus 1. Then you have another s plus 1 here. Okay. So minus. Okay. So if you see, if you want to split this, okay, this is 1. If you want to split this, you will have, if you want to further expand, is s. Um, I think I do it wrongly. Wait, I check s plus 1, s plus 1. Okay. Then you have s square. Okay. Then you have, wait, where is my eraser? Okay. So here we multiply by here. I'm teaching mathematics now. Okay. So s plus 1 over s plus 1. This is just to show how actually it can be, finally to have this, right? Then you have s plus 1. Then you have minus s uh, minus 1. Okay. Minus s minus 1. Okay. Then you have s square, s square plus 2. Okay. Because it's 1 times is 1. Then you have 2s minus s minus 1. Okay. This one. Then s square, uh, 2 minus 1 plus 1. 2s is only s. Okay. Then you have your s plus 1. Am I missing something? Wait for a while. S square 2 and then 2s. Okay. Minus s, 2s minus s, 1s. 2 minus 1. And s plus 1 is, s plus 1 is, I think this, okay, so it's square here. Okay. Square. So s plus 1, s plus 1. Okay. And you see here, this is a single s. Okay. This is a single s. So s s Oh, S minus and S plus. Am I correct? This one, wait for it. S plus S plus 1. No, it should be plus. Okay. Hmm. Wait, I think I do it somewhere wrong. Okay. Please check. Please check on this. I think I do something wrong because I'm actually want to see to you that to show to you that actually when you do algebraic manipulations, okay, you need to modify it so that uh it will look as if this will be can be derived from the original. So for example, 1 over s plus 1. Okay, so s plus 1. Okay, you have 1 here, then you have minus 1. Okay, if you expand, and then you have s plus 1. Okay, sorry, this one is this one maybe I do something wrong a bit here. I mean the algebraic manipulations. Okay, because this one still represent by 1. Okay, still represent 1, so you need to be to check. Sorry for that, sorry for the error. And then you see that later on when this 1 minus 1, you will have s plus 1 as a result. But why you need to do this 1 minus 1? Okay, why you need to do this step? Because we from the table we only have value for 1, and then we have a value, we only have a value for a table. I mean form, not value, form similar to table is 1, and also 1 over s plus 1. Okay, okay, sorry for that. This one is actually still correct, but it's not really representative of the table. Okay, representative of the table, because s plus 1 over s plus 1 is still 1. You can also later on, if you need to manipulate s minus 1 over s minus 1, this one is still 1. Okay, okay, sorry for the error. Okay, I think there is something wrong here, not sure. Okay, but still correct, but maybe this will end up a longer solution. Okay, okay, you can see here is 1 minus s over s plus 1. Okay, sorry for the for just now. Okay, my way just now, the first way is I think more longer versions. Okay, then you need to choose also wisely which algebraic manipulations. Okay, sorry for that. Okay, so you see 1 is actually when you do Laplace transform is actually st minus negative e t ut. Okay, this is you get it from the transform table. Okay, 1, you see here 1 in s domain here is actually impulse, and this one is actually EAT UT. So that's why we have E here in the exponential form. Okay, the next is find the inverse Laplace transform for this. Okay, so you can do this exercise. Okay, for example, here is 1 over s squared over 25. So you need to refer to the table. Okay, you can try this at home. Okay, you can refer to this. You see this table, you have s squared and you have some power, right? You can see the table, which one actually you have some degree of power. You can see here. Okay, but here you can see it is 1 here. It's 1. So you need to see where actually you can have this 1 here. You see, this is here. Okay. Mm, not really. It is more to when we have this 1 over s squared. Okay, it is more to this shape. Okay, it is more to this shape because um, Wait for what? I need to see s squared 25. So you see here s having power. So you must see that actually where is s having power, and at the same time we have a constant. Okay, here s doesn't have power. Here have s have power. However, this is n plus 1. Okay, it is n plus 1. For example, if you s here is 1, okay, s1, so it will be like your n is need to be multiplied with n plus 1. Okay, so you can see this is the most suitable, most lookalike. Okay, so it depends when you do the algebraic multiplication. So you see s square and omega square. So you can use this actually 5 square, right? So s square plus 5 square over times s. So you can times with s over s, for example. Okay, you can time with s over s, because s over s still means 1. Everything divided by times by 1 will get you 1. Okay, so it's actually, then you can put s here. Okay, wait for one. Okay, where is the equation just now? Okay, 1 over s square plus 25. Am I correct? Or difficult to, when I'm disable my screen share. Okay, I'm transferring to my touch screen. Okay, to my touch screen. Okay, so wait, I need to make sure that it's actually showing this screen. Okay, so where is my pen? Okay, so here you can see that it's actually given s square plus 25, right? Am I correct? Then this is your fs. Okay, so you do some manipulation, algebraic manipulation. Okay, and then you do again some some algebraic manipulation, because you need to find the similar shape. So this is still 1, right? So everything times 1, we get the same things. Okay, so we can use this, and then you have s over s squared plus 5 squared times with 1 over s. Am I correct? So see this shape from the table. So it is actually what? Let me see. From the table. Okay. So it is actually cos. Cos. mm, Cos omega t ut. Okay. Cos omega t ut. Okay. Sorry, wait. I need to write it more. I mean more clear. Okay. So here is your omega. Omega is your omega equals to 5. Okay. So cos omega, which is 5 here, t ut. Okay. Times if ut. And then you have 1 over s. So 1 over s is ut. Okay. 1 over s is ut. So you have here. So you can see, right? Okay. You can see it is cos 5t ut, because 1 over s is ut. Okay. 1 over s is ut. So this is your fs. Okay. Okay, you can try to do the others. Okay, you can try when stop sharing. Okay. So sharing and going back to the other screen. Okay, you can try to do the rest. You see here we have 2s over s squared over 10. So this is what? This is 10 is like a constant. Okay. is like constant but no power. You can see you can have what algebraic manipulation you can do. Okay, s squared plus 10. You bring to, okay, never mind, you can try first, huh? You can try first yourself. Okay, you can try for the example 2 and exercise 2 and exercise 3. Okay, bear in mind, you can see here 10 is cannot be directly converted to square equivalent, right? You cannot square anything just to have 10, right? For example, 35 you can be obtained it by 5 square, right? So here you cannot do that. Okay, so you need to refer to the table to see general form that you can able to obtain by algebraic manipulations. Okay, and then you see here there is 2s on the top. Okay, there is 2s on the top. Where is having s on the top? Here, cos omega t. Whereas, so you only have this, but sometimes this s can be cancelled out if you time with 1 over s. Am I correct? If you time by 1 over s, you will lose this s, and then you will have an only s. Okay, but it depends on how you approach these problems. Okay, how you approach this problem, you need to do some algebraic manipulation first. Okay, you try to do this and try to do this. Okay, next, properties of Laplace transform. Okay, properties of Laplace transform. Wait. Okay, the same like the others, okay, before, which is the linear operation, differentiation, integration, time shifting, frequency shifting, convolutions, and modulations. Okay, so linear operation, if you f in time domain and ft in time domain are time domain function, and a and b are constant. Okay, so you have a Laplace transform of af1t plus bf2t equals to af1s plus bf2s. So you can see this is a Laplace transform of af1t plus bf2t will translate to the same constant a b outside your Laplace transform signals. Okay, so proof. Okay, this is a proof. Okay, you see Laplace transform of AF1 plus BF2. Then you do some integration from 0 to infinity, just like you know. And then you AF1t plus BF2t times with E negative ST for the general formula of Laplace transform dt. Then you bring this A out because it's a constant. You bring this B out also because it is a constant. So you will have this F capital signal S plus B and F capital as a result of your Laplace transform. So it is showing that Laplace transform is actually a linear operations. Okay, so you can see this is example 6. Okay, find given f1 cosh. Okay, you know what is cosh? I think you learn in your mathematics as well. Not sure where is it in this table. Mm, Not sure if we have that, but you know what is cosh, right? We have also sine hash, right? So cosh 80 equals to E at t minus plus E at t over 2. Find the Laplace transform for ft. Solution ft equals to half E at t plus half E negative at t. Then you have half of L negative at t plus, okay. So this is half and you have the Laplace transform of E at t. And then you have half of Laplace transform of E negative at t. You refer this to the table. Okay, you refer to the table of the Laplace transform with a function that having the exponent function in your time domain. Here, okay, this one. So you have 1 over s plus a. So you have this 1 over s minus a. Okay, this one is 1 over s plus a. Because here you see this is a showing positive. So here is showing negative. So uh, it's actually negative. It's actually negative 1. So that's why you have it's actually when you see this formula is showing is actually for general formula for EAT. So EAT. So it's actually your A is actually negative A. This why negative A times negative, you get AT positive. Okay, here. So that's why it's actually negative A. And then this one is follow the general formula. That's why it's actually only S plus A, only plus A. Okay. So S, then uh you do some mathematical operations, okay, to obtain this. So this is exercise 2. Okay, you can try, and this is the solutions. Sorry for the interruptions. Next, we go to this second part, which is the differentiation. Okay, for higher order differential form. Okay, higher order. So you have here is d square over dt square. Then the Laplace. Okay, you see here for high order differential form, and you can see Laplace transform fair. You can see here, this is here, okay, the differentiation. You can see here, this n of ft and dn. You can see that if you have higher order of 2, you will start with 2 here. Okay, S2. If you have 3, it will be S3, and so on. Okay, and so on. And then it is in decreasing order. Okay, so if you have 2 here, means that this is S square, and then minus S2 minus 1 will be S1. And F with t, which t is 0. Okay, this is Fourier transform with S. This one is F in time domain with t 0. Okay, so here, okay, you see this is because this is HE squared. Okay, so it's SL dft minus over dt and df0, and at the end you will have this. Okay, so you can refer to the table, no need to prove this unless they ask you to do that. Okay, next, and for third order derivative, the same as well. You have S3 as the biggest number, and then S here is actually 3 minus 1, so you have 2, and then F0. And then the next one is Sn minus 2, which is 3 minus 2. You have S1, and still F, and you have F now, which is the first order differentiation of your time domain signal, okay, which is df0 over dt minus d square f0 over dt square. Okay, so in general, for n, derivative of ft will be given like this. Okay, so which you can refer from your table. So given x double prime plus 3x prime plus 2x prime equals to 0. If you can see, x double prime mean is actually dx square over dt. 3x prime is actually dx over dt first order, and 2xt equals to 0. Find xt if x equals to 0, if x with time equals to 0 is equals to 1, and x prime of when t equals to 0 equals to negative 4. So this is actually, your x equation in 0. If with t equals 0, you have 1, and x dx over dt when t equals to 0, you have negative 4. So first, what you can do is that you can see, okay, this is given, okay, this is given dx square, okay. So you have the largest, which is dx square. So you refer here to obtain the dx square. So that's why you have this, okay. This is the results of dx square over dt for the Laplace transform. And then you have 3x square, you have this, okay. And then the 2xt, we just put 2x or 2xs equals to 0, okay. Sorry, this 0, it should be here, okay. And then put in the value of initial condition. This is why we refer to initial condition, because it is t equals to 0, okay. So you put this value and then you obtain the solutions, okay. And then you do some algebraic manipulation, then you obtain that results of inverse Laplace of a x Laplace transform signal. You have xt, which is equivalent to 3e negative 2t minus 2e negative t, okay. So you can try this exercise, okay. Y square, y double prime dy square over dt plus dy 2y dt plus yt, okay. And then given with these initial conditions, then try to solve it, and hopefully you can get this value, okay. Next, integrations, okay. Next is integration. The integration properties can be used, okay, if you fs, if your Laplace transform fs is the Laplace transform of ft, okay. You can see for the integration, Laplace transform of an integration time domain signal from 0 until t is actually equivalent to f over s, f in time in Laplace domain s over s. So you can see integration given here. Okay, is given. Okay, here is d 0 to t and f tau d tau, which is fs over s. Okay. So you see here, okay, so proof, okay, this is some proving, okay, you can refer. And this one is actually you learn since your school, right? This udv equals to uv minus integrations of vdu. Okay, this is one is by substitutions. I think you guys know, right? I hope it is shown here, but you can refer to the table for the mathematics here, okay. But I'm not sure if it, I mean, I'm sure that you can do solve the question faster if you actually have this, this is actually basic mathematics in your head already, okay. If you have that, it will be faster, but if not, don't worry, table is given, okay. Because engineering is not about it's not about memorizing, it's about understand how to use it, okay. Where was I? Okay, so integration from infinity to from 0 to infinity, right? Because this is Laplace, right? General formula. And then time is your negative st dt. Okay, this is Laplace general formula. And then this is your time domain signal in the integration form. Okay, then you do the integration accordingly. Okay, then you see here, okay, you have negative st dt, you can put out because the integration is in the time domain signal. Okay, then you have ft dt from 0 until infinity. Then next is 1 over s, okay, t0 ft negative s dt. Okay, because you see here, right, you can see this okay, you try to use this general formula. Okay, you try this general formula, and then in the end you will have your fs over s. Okay, this one wait I just want to see if this is correct, and this way of is it correct, or is with error or not. Okay, I think no, hopefully it's okay. Okay, next we go to the time shifting operation. The integration properties can be used if your fs is the Laplace transform of your ft. Okay, so for example, if you have Laplace transform with a time domain signal which undergo time shifting, okay, is equals to negative e t naught s of fs. Example, find Laplace transform for this impulse. Okay, you see here ft is equals to 1 between 0, t and c. Okay, you see this is impulse, right? Maybe so ft is 0 for other t. Okay, if you have other value of t, f is 0, so this is impulse. Okay, so you see ft is equals to ut minus c. This is actually how you obtain the impulse, right? Okay. Mm. You know the standard ut is like this, right? Am I correct? And then you minus with ut minus c with a time shift. Right, you minus with a time shift. Okay, let's say you have uh, let's say you have your c here. Okay, it is actually shifted by c. Then you minus with this and minus with this, you only have a value. Okay, you have only value at your c. Okay, for example, which can be your impulse. It's very small, but other than this, it is actually 0 for the rest. Okay, for the rest it is 0, but we only have value at the one value of time. That's why it is an impulse, very short time. So ut minus c. Okay, then Laplace transform of ut minus c. So you separate this L with ut and refer to your table of Laplace transform. You have ut here is 1 over s. Okay, that's why you have 1 over s. Okay, and then ut minus c with a time shift. So you see something somewhere if we have time shifting here. Okay, you see a function with time shift ft minus t0, so it's actually fs equals to times est0. So that's why minus ecs. Okay, minus ecs because we don't know what is the value of our c. Okay, okay, here, okay, t0 is actually s. Okay, I think it's okay. I think it's okay because and wait, I need to see ut as a 1 over s. Yes, I'm correct. And then the time shift will represent by negative st0. So it's this. I mean, I confirm this is correct. So negative cs time over 1 over cs because one is this one is actually ut, and this one is to show the time shifting with to the unit time step function. Okay, in the time domain. Okay, now is in the Laplace domain. Okay, example 8. Okay, given fs 2 over s squared minus 2 negative e to s over s. Find inverse Laplace transform for fs. Solution, okay, from the table. Okay, you see, then you refer to the table. If ft is equals to t, then fs is equals to 1 over s squared. You can see this is the general equation that we can relate with this. You see here is 2s squared. Okay, you can bring the 2 out, and then you in bracket you have 1 over s squared, which is the fs. Okay, and then this one you try to see the related function where you have actually exponent and you have s on the top. Okay, so you can manipulate, you can manipulate which is this one also have negative exponents. Okay, and this one also have negative exponents, so you see which one actually relates. Okay, but this one we have s square on the bottom. Okay, on the bottom you have that. Okay, sorry, this one is f here, f1s, this one is f2s. Okay, sorry, this the f here is suddenly dropped down. Then you see that you obtain here 1 over s. Okay, is actually 2t. Okay, because question is inverse Laplace. Okay, then 2t minus square. Okay, 2t minus 2. Okay, You can see here E negative 2s. E negative 2s is actually with a time shift elements. Okay, here. Okay. Okay, so this is exercise 4. Okay, you can try. Okay, consider the exponent function which has the equation of ft equals to 5 exponent negative 0.30. So if you can see, this function is delayed by 2 seconds and multiplied by ut to become this. Okay, find Laplace transform for f1t. Okay, so you can try this. Second, you see this is a unit step with a delay of negative 2. Okay, with negative 2. So this having time shift. Okay, try to do that. Okay, so you need to find Laplace transform for f1t. So it's really f1s. F capital F, 1 and s. Consider another exponential function with ft equals to 5e negative 0.3t ut minus 2. So find Laplace transform from f to t. Okay, you can try this also. Okay, you see here there is a time shift here. Okay, you see here, okay, when you have delayed by 2 seconds, you have t minus 2. Okay, you can see E also here will be delayed by t minus 2. Okay, because it need to follow this to follow unit step is the originally is from 0, right? But now we actually, I mean, unit step we have value of 1 from starting of 0. However, if it's shifted, then this is also will undergo some shifting. Okay, new function here. Consider another exponential function ft negative 0.3t ut minus 2. Find Laplace transform for f2t. Okay, we try this at home. Okay, it's shown here. Okay, no need to. Okay, you can try this at home. Then you see if the solution actually same with your answer. Okay. Okay, you see here. Okay, so t equals to 0 is 2, a equals to 0.3, so negative 2 sfs. Okay. Okay, I think you can see this for yourself, okay, because it's actually quite straightforward. But I suggest that you do this first, okay? You do this first and check your answer after that. Okay, then we go for this frequency shifting. Okay, so frequency shifting, if ft has a Laplace transform for of fs, okay, then L, okay, this is frequency shifting. L Laplace transform of e at t ft equals to fs minus a. Okay, here exercise for you. Okay, you can try. Find yt if ys is equal to s over s squared minus 6s plus 8. Okay, so if you can see first from here, actually s here can be factorized first. Okay, factorized is, if I'm not mistaken, s minus, in bracket s minus 2 times bracket s minus 4. Okay, bracket s minus 2 times bracket s minus 4. Okay, and then you have s here. Then so try to solve this. Okay, then you will obtain your yt. Okay, this is the inverse Laplace transform. Okay, you see here from the ys to do the to obtain the time domain signal. Okay, Yeah, okay, you can refer here. Okay, can refer, I think is here. Okay, it's related to this one. Okay. Mm, where was I? Okay. Now convolution. If f hash, okay, convolution, right? If hs equals to fsgs, then the inverse Fourier transform of hs, okay, is a convolution between f and t. You know, right? As I told you, convolution in time domain is more messy, complicated. That's why we do in frequency domain. Okay, because in frequency domain it's just multiplication. The same goes in Laplace transform. Okay, conversion of f dgt is actually just a multiplication in your Laplace domain. Okay, here is fs times your gs to obtain your hs. Okay, the next is modulations. Okay, the multiplication of the function xt with sine omega t or cos omega t. Okay, if xt uh, undergo Laplace transform to obtain x domain S signal. Okay, Laplace transform signal for all real value of omega. Then xt sine omega t, you see here. The modulation here is the carrier. Okay, we introduce carrier, okay, to our signal. Okay, this is your information signal. This is carrier times sin omega t. Then you have this form. And likewise, if it's cos, you will have this. So this one you can refer to the table. Okay. So with this, with that, we finish our chapter 4, part 1. Okay. Thank you for listening and see you in the next lecture. Thank you.